All right, hello and welcome. Today is Thursday, April 30th, and it is the last day of April, and we're moving on to May, the final month, tomorrow. Thanks for tuning in. Today we're going to review for our Unit 10 test that is coming up, and the test is, of course, on Monday. You'll see on Canvas we have a new homepage and all that. Of course, you can click on the link modules to go back to the original page, so you can go through the modules. There are also announcements. I wonder if you guys get those announcements. I started using those, pushing out announcements through Canvas. We'll see. I think you get like a little icon thing on the left side or something when you get an announcement. Let us begin by talking about some of the misconceptions we have, starting with the labs that I graded over the last couple of days, and then we'll move on to the study guide. Let's see. Is anyone here? We have a couple of people. Chupido's back, but our numbers are dwindling every day. It's a sad situation. Maybe we just have too many streams, and I might start cutting back on the streams, so it's not stream every day, because you know, people are getting tired, it seems, of watching. Dennis will be late for a little. Oh, okay. Probably grabbing his cereal. So let's see. Let's draw some quick circuits. Here is the series circuit. And here is our parallel circuit. I'll draw it this way. Whether I draw it this way or the other way, it doesn't really matter. These are the same thing, so let me show you. So if I drew it the traditional way, okay, so these are the same thing. Okay, just look at the current flow. Current comes in, and then it splits apart into three pieces, and then they recombine again. So that makes all three of these parallel. Same thing with the other one. I mean, when it gets to this junction here, it'll keep splitting into three parts. Is this thing a junction? Is this thing a junction? Well, this entire place, this entire spot is a node. This is a node. So you can just squish it into a dot and combine all three resistors at the top end, and then squish and combine all three resistors at the bottom end. This is a node 2. Alright. So a node, remember, is a region where the potential is the same. This has the same electric potential. Has the same electric potential. Oh. Okay, so In the series circuit, of course, you only have one pathway, whereas in the parallel circuit, in this case, you have three different paths to take. You can take the first route, you can take the second route, or you can take the third route. Okay. And thus the current splits up into three parts. Most of you did fine on the first lab, the series lab, where you said the voltage, the current is all the same. I total in this case, because I total, of course, is the current that comes out of the battery. This is I total. Okay, and since that same I total goes through each resistor, R1, R2, R3, then the current for each individual resistor was the same, I1, I2, I3, right? And we also have to explain what the term voltage drop means. Voltage drop happens across the resistor, not between resistors. A voltage drop, and it doesn't mean your voltage of the battery is changing. It means that whatever the battery voltage is, V, okay, after gaining V by going through the battery, you're going to lose, your voltage is going to drop, you're going to lose a little bit every time you go through a resistor, across it. So as you jump from one side of the resistor to the other, your voltage V is going to drop by some V1 amount. And that's what voltage drop means. Right? So when you jump through resistor 2, I shouldn't say jump, but travel, when the charges travel through it, it'll lose some of its electrical potential energy. So it loses some potential. Oh, V2. And the same thing over here, V3. So that's what voltage drop means. It's basically the voltage, the individual voltage of each resistor. Okay. And so we can do loop rules where after gaining the battery voltage, we subtract V1, we subtract V2, we subtract V3, and we end up with 0 volts. And this leads us to the fact that all of the voltages, when you're in series, add up to the total. Okay. So when you're in series, the voltages split up into parts, and of course the sum of the parts is the whole. And to find the individual parts, you have to use Ohm's law. Ohm's law is V equals IR. So V1 must be I1 times R1. V2 must be I2 times R2. V3 must be I3 times R3. And since all of the I's are the same, all the I's are the same, I'm just going to call it I. This is I times R1 plus I times R2 plus I times R3. And then when you factor out the I's, you can see how rec is equal to R1 plus R2 plus R3. So to find the total resistance, of course, we can just add all the resistances. Not only that, this shows you that each individual voltage, the voltage drop, if you will, V1 for example, is dependent or directly proportional to the resistor. Right? V2 is directly proportional to R2 because I is the same for all three elements, so I doesn't really matter. What's going to determine your voltage drop, or the amount that it takes up, is the resistor. So V is proportional to R. This is the proportional symbol. okay, which is directly related to each other. So when you increase R, you increase V. Now the other way does not work. When you increase V, you don't necessarily increase R, because R is dependent on physical property. So R is a physical property. Okay, so when you increase V, you're actually going to get more current, I. You're not going to get more resistance. So in order to get more resistance, you have to change the resistor itself. If you make the resistor hotter, perhaps you might gain some resistance, but you know, not as much as swapping out the actual material. When you increase R, you increase the voltage drop. I shouldn't say voltage, because voltage can represent many things, right? You're not changing the voltage of the battery, that's for sure. When you increase R, you're changing how much is going to drop at that resistor. So you're not changing the voltage of the battery, you're not changing the resistance of the resistor. If you increase V, right? If you increase the battery voltage, you get more current. If you increase the resistor, you're going to get more voltage drop for that resistor, but the sum is still, or the sum of all the voltage drops still has to add up to the total. Okay, it's just the bigger resistor will drop more voltage. Bigger resistor will drop more voltage. Okay. Now this leads us to the actual light bulb questions now. Okay. So at the end, it's at the lab state. Now if I replace all these with light bulbs, remember light bulbs are just like resistors, except they glow. Okay. When the light bulbs are on and they're hot, they're working, they work just like resistors. Of course, when they're not on, they're cold, they have very little resistance. And then when you turn it on, it heats up and it gets a ton of resistance. Each light bulb can have a different amount of resistance, right? When you go to Home Depot or something and you try to buy light bulbs, you get all sorts of light bulbs. And they draw different amounts of power. And the power is directly related to the brightness. Right. Now power has many equations: IV, I squared R, V squared over R. And you want to use the equation that is suitable for your circuit, right? So when I compare brightness in a series circuit, I want to use this middle one here. I'm going to use P equals I squared R, not the other ones. Okay, that's because I only want one variable that is going to change. Sorry, I should say that it's going to determine the power output of each light bulb. Okay, not the system. The system is, you know, whatever the system is. Now this is if I were to do P1, I would do I1 squared times R1. So P1 will help me determine the power of light bulb 1, and by finding P1 we can see and compare it to P2 and P3, we can see which one is the brightest. Now because I is all the same in a series circuit, that's why I chose this middle one. Okay, we know that I is all the same for all of them, so you don't have to write I1, you can just write I. Right? I1 is I, and P2 would be equal to the same current squared times R2. And now you can see how the power, because just like voltage, the power is directly proportional to the resistance. Okay, so this means that if a resistor has more resistance, it's going to draw more power, which means it's going to be brighter. It's going to be brighter in your circuit when you are in series. Let me see if I can pull up our FET simulation and then start doing it. The goal of the lab was for you to actually experiment, but not a lot of you actually experimented. You know, some of you just rushed the assignment, tried to get it done, and then didn't really learn anything. I mean, you got the work done, but didn't really learn much from it, so it's kind of meaningless. So the simulator allows you to use resistors or light bulbs, right? So here's a battery. Let's put the battery in, and then we'll put light bulbs in series. Now to connect light bulbs in series, you go from one end of the light bulb to the next. So the charges go through the bottom of the light bulb. It goes up through the little filament inside, and then goes down and then through the side. Okay, if you watch the first or second, I can't remember which video, on circuits, remember there's the light bulb challenge video I showed you from MIT. We talked about how to connect wires to light bulbs, which is a very important skill to have. I know one student makes a bunch of money changing light bulbs for like old people that can't do it. So consider, you know, being an entrepreneur and use your physics education to get a job. All right. So here's our circuit. Let's change the voltage a little. We'll use 30 volts like we did in the lab. Alright, so of course these light bulbs have the same resistance, 10, 10, 10, and so their brightness is all the same, right? Now if I compare this to having just one light bulb with a 30 volt battery, here we are. Okay, chat. Is this single light bulb going to be brighter, just as bright, or dimmer than the 3 that I have above? Answer in the chat below. Right, before I connect it, make your predictions. Oh, we have a lot more people watching now. That's cool. Yeah, y'all hear me? I'm about to turn on one light bulb. Is it going to be the same brightness, just as bright, or dimmer? Ooh, not as bright here. Oh, okay. Oh, there we go. Someone heard me. Oh, just as bright, eh? So we got one just as bright. Anyone for brighter than the 3? I'm about to connect it. Interesting. Remember, this is in series. All right, let me make sure the values are the same. Remember, this is 30 volts, 30 volts, so the battery's not different. These are 10 ohms, 10 ohms. This is 10 ohms. All right. Okay, so the light bulb is the same. So I connect 3. Now in series, they have to share the voltage. The voltage drop, so whatever this 30 is, right? This is 30. The voltage drop at the light bulb is 10 volts. Each bulb is dropping 10 volts. So it's 10, 10, 10. That adds up to the 30 volts. So each light is only getting 10 volts. But how many volts is this light bulb getting? Well, this singular one is getting all 30 volts. All 30 volts. And so, kablamo, it is way brighter. It is way brighter. Okay. Now we can, of course, use our equations to actually solve this, and so we don't have to guess. Okay, let's see. Let's solve this. If I had 3 light bulbs with the same resistance, then with same R, then our P1 is equal to, of course, I squared R, right? But what is I squared? Well, I is the total current, and it's equal to the total voltage V divided by the total resistance. So that means the current is actually dependent on how many elements you have in your system. Since you have 3 light bulbs, you're going to have 3 R's worth of resistance. And so your current is only 1/3 of V over R. With the same R with 3 bulbs, R with 1 bulb. Now in the 1 bulb case, the I total is equal to the battery voltage divided by, now the rec is only a single R, and so it's, you know, the I is actually 3 times bigger. It's 3 times more current, but because I is squared, you're going to get 9 times the brightness, 9 times the power. Okay, so let's plug this in. Let's see, this P1 would equal 1/3 V over R1. Oops, I'll just say R. Continue. Times R. This gives me 1 over 9. V squared over R times R gives me V squared over R. Over here I have just V over R squared times R, where power is I squared R. And so we get V squared over R. So this is, as you can see, with a single bulb, you're 9 times brighter. Okay. Let's go back to our simulator. Now, let's have different resistances. So if my resistance are different, so this is 10, let's make this second one 15. Let's make this one 30. No. Okay, 30. Ooh. There's too much going on. Let me turn this one off. Off. Alright. So this is 10, 15, and 30. When you're in series, remember the power is proportional to the resistance. Meaning, the one with more resistance is going to be brighter. So when you plug stuff in series, whichever has more resistance will get more power and it'll be brighter. Now the voltage is shared, so the other ones kind of drop. With more resistance in the system, there's less current overall. Okay, there's less current overall. All right. So when you have a circuit, you know, and it's in series, then having one bulb is going to be better because the voltage doesn't split up. Notice how if I do one bulb with 15, it's still brighter. One bulb with 30, there it is. One bulb with 30 ohms is still brighter than having the 30 ohm light bulb but in series with 2 other ones. Okay, you see, when you're in series, having other things being on, having other elements in your circuit will affect your individual element. Every element is dependent on every other element, and this is why when you have houses, when you're doing the electrical systems in houses, you don't want your connections to be in series. Okay, you want all of your connections to be parallel to each other. Okay, that way, when someone plugs in their light bulb or their computer in one room, and then someone downstairs connects their blender or microwave in a different room in the kitchen or something, okay, it will not matter who's using what. All devices will get the same voltage and therefore will operate the same way. Now, of course, there's a limit, because as you continue to plug in stuff into the wall, you start using more and more of the current, and that might blow a fuse, right? So that's the other thing. All right. Now, if you keep adding more and more elements in series, are you ever going to blow a fuse? If you have a fuse box, remember the fuse box is right outside your power source. So remember, someone's room has a little fuse box in there. And so when you're in series like this, when you're in series and you keep adding stuff, okay, would you ever blow a fuse? No. The reason why it's no is because if you keep adding stuff in series, you're going to continuously increase the overall resistance rec, and since rec goes up in series, the total current will always go down, and therefore it's less and less likely to blow a fuse. So there's your small benefit, minor benefit, but of course the negative far outweighs the positive for series circuit. The negative is that everything is dependent on each other, and and the power delivery is not as much. Okay, now let's compare this to our parallel system. So why is parallel so much better? Well, with three pathways, now our currents add up, but our voltage remains the same. You can see how each battery is each resistor is touching the top and bottom of the battery. So that means these resistors are parallel to the battery itself. Therefore, voltage V of the battery must equal voltage 1, must equal voltage 2, must equal voltage 3. And this is independent of the value of each resistance. So it doesn't matter if R1 is smaller or R2 is bigger, etc. It is independent of the resistor. Okay, this is just facts, as you guys say, facts, that no matter what the value of R is, the voltage drop or the voltage of each resistor is going to be the same. And that is because when you're in parallel, you can only take one pathway at a time. And so if you do the same loop rule, so if I did a loop rule, I would have to do 3 loop rules. One for the green, one for the blue, one for the orange. So the blue one tells me that V minus V1 equals 0. So V equals V1. The green pathway tells me that V minus V2 equals 0, and therefore V is equal to V2. And the orange tells me that V minus V3 equals 0, and so V equals V3. And this is how we get this this fact. It all comes from Kirchhoff's loop rule. We're not really using his name in this class very much, but that is the scientist who figured all this out. Kirchhoff. Spelled really weird. Let's see. Kirchhoff. There you go. That's his name. Kirchhoff. So this is Kirchhoff's loop rule. And he was the one who figured out all of this stuff. Alright, so we know that the voltages are all the same, and because the current has to split up, the current now adds to the total. I, which is I total, I is equal to I1 plus I2 plus I3, the individual currents. And I is directly proportional, I shouldn't say directly, is inversely proportional to the resistance. How do we know that? Well, again, that comes from Ohm's law. Ohm's law would tell you that the voltage in resistor 1, V1, so this is, yeah, V1 would equal I1 times R1. Okay, now if I solve for I get I1 is equal to V1 over R1. Okay, but V is all the same, meaning I2 is equal to V, the same V, over R2. Right? And since V is all the same amongst all the resistors, then we can say that each individual current is directly proportional, is proportional to, not directly, but is proportional to the inverse of R, or is inversely related. Okay, this tells you that when you're in parallel, the resistor with more resistance will get less current. The resistor with more resistance will get less current. The resistor with less resistance will get more current. However, the individual current still has to add up to the total. Now, when you're in parallel, the rec rule is different. Remember, in series, we could just add up all the resistances, but in parallel, we can't do that. With parallel, we have to do the 1 over 1 over, so 1 over R1 plus 1 over R2 plus 1 over R3, dot, dot, dot. We have to inverse the sum of all the inverses. Inverse of the sum of inverses. Now, and finally, let's talk about light bulbs again. Power. Okay. Since voltage is all the same, we're going to use V squared over R to talk about the brightness of bulbs. Again, we do this strategically because V is all the same, so that we are only looking at one variable. And so you can see how P is related to 1 over R, just like current. So in the series circuit, power was related to R directly. More resistance, whichever element has more resistance will have more power, therefore will be brighter. Okay, so here we have inverse relationship. Whichever element has more resistance will actually be dimmer. Okay. Now there is another way to look at it. If you try to use the I squared R equation, it's a little bit trickier, it's a little harder, but you'll still get to the same spot. And that is, you know, hey look, if R increases, it looks like power is increasing, right? But that is not true. That's because if R goes up, then the current that goes through your resistor actually goes down. So now you have a inverse relationship between current and resistance. This is why I didn't use this formula. I used V squared over R because we know that V stays the same. But you can still use it. We just have to think a little bit more. So if I have more resistance, that resistor in the parallel circuit will actually get less current. But the equation tells you that the current is squared. So the impact of having less current is more in this case, meaning having less current matters more than actually increasing the resistance. Okay, the decrease in current is directly proportional, but the power is exponentially related to current, meaning the impact of current is higher than the impact of resistance. Okay, and therefore power will decrease. So you arrive at the same conclusion in that when you increase R, you decrease power. Okay. So let us go back, boom, and let's reset reset all of this. Now let's create some circuits. We'll do one light bulb with, let's still use 30. Can I just type? No, I can't. Darn it. 30 volts. All right, one light bulb. Let's connect it. Remember, it's one at the bottom side and one on the side of the light. Those are the connecting ports. You see how there's like a metal part at the bottom, and then there's a black strip. The black strip is insulating, so it separates the side from the bottom. It's there we go. And then we have light. Whoa! Let's turn that off for now. Okay, so now let's create a system with 3 light bulbs that are in parallel. Whoa, this is going to be a little harder, right? I think it might be easier if I tilt them. How do I tilt them? There we go. Let's tilt them this way. Oops. I'll tilt them like so. Okay. I need the bottom side, all the bottoms to be connected to each other and all the tops to be connected to each other. So when I say bottom and top, for light bulbs it'll be bottom and side. So here it is. So when you connect something in your outlet, right? Even though your little 2 prongs are oriented horizontally, you can think, tilt your head sideways, and so each connector port is actually touching one side of the light bulb, each little prong. Okay, now I want to connect all of these together, so all the bottoms of each light bulb are connected, and then the sides of each light bulb is connected. Okay, so the current has to go through one side, one end. Let's do it this way. Just now that I think about it, I could have done it in vertical orientation, but too late now. And let's make sure that we have the same voltage. Okay, so 30-volt battery, right? So chat, you following? Let me ask another question here. 30-volt battery for both. Each light bulb is the same, 10 ohms, 10 ohms, 10 ohms. Okay, so here it is with one light bulb. Boom, you saw how super bright it is, right? Now the question is, how about the brightness of the 3 parallel ones I have down here? When I connect the battery here, is it going to be just as bright, even brighter because I have 3, or is it going to be dimmer because I have 3? Alright, answer now before I connect it. Brighter, just as bright, or not as bright? Take your guess before I connect it. Or, you can use your equations to solve for it. Ay, ay, ay. All right, let's see. 3, 2, 1. Boom! Oh my gosh, what is going on? Well, it looks like every single light bulb has the same brightness. Same brightness. Only because they all have the same resistance. Okay? Every single light bulb. So if you're using the same light bulb in your home, the same style of light bulb, right? That light bulb is going to have the same resistance. So whether you plug it in your room, or you plug it in the kitchen, or you plug it into the living room, that light bulb is going to give you the same amount of light because the circuit in your home is all parallel. Okay. Now, of course, you might have noticed that if you have different kinds of light bulbs, different light bulbs have different power ratings, and therefore they give you different amounts of light. Their wattage is different. So let me turn this off for now. Boom. And now let's change the light bulbs. So they're not the same company, or they're not the same style. We'll keep the 10. What numbers did we use before? 10, 15, and 30. There we go. 10, 15, and 30. All right, now take a guess. Now that I have different light bulbs, how will it behave? Chat, your follow-up question. We changed the light bulbs so they are different kinds. The 10, a 15, and a 30. How will their brightness compare? Okay. So let's see if we can predict it. So that's the whole point of getting these equations, so we can make predictions. Well, the prediction, let's see, power, we said, is equal to V squared over R. And V is the same, even though the resistors are different now, V's are still the same because they're parallel, and parallel resistors have the same voltage no matter what the value is. And so P1 must be V squared divided by R1, and P2 must be the same number squared divided by R2. Okay. So P1 is 30 squared over 10, whereas P2 is 30 squared over 15, and P3 is 30 squared over 30. Okay, so looking at the values, this is 30 times 30, that's 900. 900 divided by 10 is 90. Right? So this is P1, P2, P3. What's 900 divided by 15? Well, 15 goes to 90 how many times? 1, 2, 3, 4, 5, 6. So 60. And then this is 900 divided by 30, so 90 over 3, that's 30. Okay, so this is 90 watts, this is 60 watts, this is 30 watts. So as you can see, of course, we already talked about it, the one that has a bigger resistor will actually get the least amount of power, and power is basically your brightness. So let's see now with the different resistors. Remember, this is 10, the first one is 10, the second one is 15, the third one is 30, and we connect them, and voila. It's so hard to see. Let me turn this one off. How can we know? We have to look at the size of the ray. Maybe I'll lower the voltage a little bit so it's easier to see. Let's make it 20 volts. Let's make it 15 volts. And we'll cut the voltage in half. Well, voltage is the same, so it's going to drop it proportionally. Okay, now it's easier to see the lines. So you can see how the 10 ohm resistor, so I should say 10 ohm light bulb, has the same size line as before. The 15 one is slightly smaller, and the 31, of course, is the smallest. So least bright, second least, and then this is the brightest, or I should say second most, and then third most. And again, whether you have a single bulb or multiple bulbs, or multiple bulbs with different values, the light bulbs that have the same value, like this 10 ohm here at the top when it's in a single bulb setup, or this 10 ohm resistor that is in an entire system of light bulbs but with different values, because they have the same resistance, this 10 and this 10, they actually have the same brightness. Only these two. That is profound. See? So how does this make sense? Well, think about it. Let's say you turn on one light in your room, in the entire house. Okay? That light bulb is going to have a certain amount of brightness. Okay? So when you turn on another light bulb in a different room, the brightness of your bulb is not going to change. It's not going to change. Okay? So whether you have all the light bulbs on or not does not matter. So let me show you what it means. So let's say you turn off a light bulb. When you turn off a light bulb, you are turning off one of the connections. So let's say in the you turn off all the lights in your kitchen, boom. You turn off the lights in the living room, boom. So the only one that is on is the one in your room. And notice how the brightness of this one did not change. Okay? It is independent of the other elements. So in series circuit, they are dependent on each other. If you turn off one light bulb in series, it's going to turn off everything. So let me show you now. So let's say I had a series circuit with two light bulbs. Oops. So well, I can do 3, I guess. You'll see 3. Notice I have to crisscross the connection. It goes through the bottom, through and then out the side, through the bottom, out the side, through the bottom, out the side. There we go. Boom. Of course not as bright. Look, as soon as you turn off one light bulb in one room, it cuts off the connection for everything else, and it turns off all 3. Whereas in the parallel system, okay, they work independently. Okay? That's because you still have a closed loop for the charges to flow. But in a series circuit, there's only one pathway. So if you cut off the pathway at any point, it's not just because it's in the front, it could be anywhere. If you cut off this pathway, it turns off everything. All right. So I guess that is it for the discussions. Oh. Well, I suppose that's it. You're going to study. We'll see if we can do a quiz bowl or something tomorrow. But we do need people to show up. If people don't show up, then we can't do it. Then I'll just cancel the stream. So tell your friends, tell your buddies to wake up tomorrow. Thanks for tuning in. I'll see you next time.